Hello everyone. We are now going to begin our lecture on drawing inferences for two population means. We previously learned how to draw inferences from one population. However, this time we will be studying two different populations. So there's going to be two separate populations which we will call population 1 and population 2. So there'll be two different populations, and then from each of these populations we will be drawing two samples. So there'll be sample 1 and sample 2, and we will be surveying them for the same question. So the variable that we are studying is going to be the same, and the survey is going to be the same question is going to be sent to sample 1 as well as sample 2. And once we collect our data from each of these samples, we are going to perform our descriptive study, that is, find the mean and the standard deviation. So the next part is descriptive measures. All right, so uh, mean from sample 2 and standard deviation, same thing for uh, sample 2. And then once we have our descriptive study done, what we are going to do is we are going to compare the two means. So compare the two means and come to a conclusion whether the mean in population 1 is greater than that of population 2, or if it is less than that of population 2, or there isn't any difference at all between the two means of the population. All right, so we are going to go through the step-by-step process of performing this kind of study. All right, so there'll be, of course, different rules for the distribution, all right, as well as different formulas, distributions, and so on. Now, here are some of the topics that we are going to learn about. The first thing is understand the difference between independent and paired populations and therefore samples. All right, so there can be two kinds of populations: independent populations and paired populations. So we are going to understand the difference between the two, and then we are going to talk about the sampling distribution. Before we perform any inferential study, we have to look at the distribution of the two means and so on. Then we are going to learn about the two types of tests we can perform on two populations. One is called the pool test. In the pool tests, we combine our standard deviation, and we can use that procedure only if the standard deviations of the two populations or the two samples are close enough, are almost equal. And the non-pool tests, uh, or the non-pool procedure, is used when there's a wide difference between the two standard deviations. We'll go through that. And then finally, we have a special study for paired populations. There's a different approach we have to take when we work with paired populations. So let's go through the next few slides, starting with understanding what independent and paired samples mean. Now, the procedures that we are going to use to perform the inferential study on two populations will depend on the nature of the two populations. Now, one type of population is called the independent population, and in this kind of population, the sample selected from one population has no effect or bearing on the sample from another population. So there's no inherent relationship between the samples of the two population. In other words, let's say we are performing a study to compare the SAT scores. All right, so let's say our study is about the difference in how students perform in the SATs in the northeast of the country versus in the west of the country. All right. So we have two different populations. One is, all right, population one, let's call that the population from the northeast US, and population two is from the western part of the country. And from each of these populations, we will draw sample one and then sample two from population two, and that sample will be uh, students chosen from the western part of the country. All right. However, there is no relationship between the the students selected from the northeast versus the students selected. They don't know each other. There's no natural relationship. They are not related. If at all they are related, then it's completely by chance, all right, by fluke. Uh, and that is what independent population means. All right. The samples, the items or the people in these samples have no natural relationship. They have no effect on each other. They are completely independent of each other. They don't even know each other. So that's what independent population is about. Paired population, on the other hand, are samples where the there is a natural relationship. All right. In paired populations, the samples are naturally paired. So if we want to perform a study to compare husbands and wives in a household, so in this case, we'll have population one, which will be all husbands chosen from a different households, and population 2 will be wives. All right, will be all the wives. Now from population 1 we will of course derive sample 1, and from population 2 we will have sample 2. And in each of these sample, if we choose a particular husband, then in sample 2 we have to choose the same husband's wife. All right. So uh, we since we are comparing the husband with his wife, we have to make sure in sample 2 there is the wife of the husband chosen from samples or chosen in sample 1. All right. Likewise, if we want to compare the uh, behavior of, let's say, brother and sister. All right. If we choose a brother, if there's a brother chosen from population 1, we have to make sure that his sister is also appearing in sample 2. So there is a natural pairing going on. All right. Here they are related. Because the study is comparing a brother and his sister. Right. Now, it does not always have to be people, it can be plants, and we will do some further study. We'll go into the different kinds of paired populations when we work on some examples, but that in a nutshell is what the difference is between independent population and paired populations. Now, a few things about creating samples from independent populations. Now, one thing we can note for independent samples, the sample sizes need not be the same. All right, so we can have a particular sample size from population 1. In this case, we see they have chosen a sample size of 2 from population 1. From population 2, we can create samples of a different sample size. So in this case, they have created samples of size 3. All right. So we have in the first population Tom, Dick, Harry, and in the second population Cindy, Barbara, Danny, and Nancy. Also, and although population 1 is a population of men and population 2 is a population of women, these are independent. All right. It's not like a husband-wife relationship. uh, it's not paired or a brother-sister relationship. It is, since it says it's independent, there shouldn't be any connection between the the items or the people in each sample. They are not related to each other. They are completely independent of each other. And that's the reason why the sample sizes, okay, the sample sizes can be different. Okay, can be different if that's what we want. Now, what they've done here is the population for population 1. Let me write that down too. All right, this is population 1, this is population 2. From population 1, they have decided to choose a size n equals 2. And Tom, Dick, and Harry are in the population of population 1. So they have created all possible combinations of size 2 from population 1. So the first one is Tom and Dick, then is Tom and Harry, and then finally we have Dick and Harry. So these three are the complete set of possible samples of size 2 that can be created from this population TD, TH, DH. Now for population 2, they have decided to use a sample size of n equals 3. All right, so they have come up with all possible combinations from this population. The population size is 4 here, but the sample size is going to be 3. So they have come up with all the different combinations, all possible samples that can of size 3 that can be derived from a population of size 4. So CBD, Cindy, Barbara, Danny, then CDN, Cindy, Danny, Nancy, CBN, which is Cindy, Barbara, Nancy, and finally BDN, Barbara, Danny, Nancy, and then they have put these combinations together. All right, so what they've done is they've created TD with combined TD with CBD, TD with CDN, TD with CBN, and then TD with BDN. So these are the first 4. And then they have done the same thing with TH. So they've combined TH with CBD, TH with CDN, TH with CBN, and TH with BDN, which are these 4. And finally, they've done the same thing with, let's take out another color here. All right, with DH. All right, so each of these have been combined, and these are all the possible samples. All right, so 4 times 3, 12 possible pairs of independent samples. So this is one way of coming up with independent random samples, okay, and where we can use different sample sizes for the 2 different samples that we derive from the populations. Now this slide presents an overview of the notations for population 1 and population 2 and the different metrics that are associated with each of them, and it's very important to make sure that we don't mix up the 2 metrics. All right, that population 1 has its metrics aligned to it and population 2 has its metrics aligned to it, because if we make a mistake and interchange the metrics, our study will be completely wrong. It'll go down the wrong path. All right, so we have population 1, population 2. We first have to first identify what we want to place in population 1 and what population 2 is going to consist of. And then the population mean from population 1 is going to be denoted with mu sub 1. The subscript denotes that this particular mean is associated with population 1. Mu sub 2 will be the mean coming from the population mean coming from population 2. Population standard deviation sigma sub 1 And for population 2, it's sigma sub 2. For sample mean, x bar sub 1 is the sample mean obtained from the sample associated with population 1, and x bar sub 2 associated with the sample mean of population 2. Sample standard deviation, S sub 1 and S sub 2. And finally, sample size is N sub 1 and N sub 2. So we always have to keep them separated when we note our data for each of them, and make sure that we don't mix up. All right, we shouldn't put N sub 1 as the sample size for sample 2 and so on. All right, so we have to be careful about that. Now in this slide, I'm going to show you how to perform a comparative study, the approach that will be taking to perform a comparative study. Okay. Now, when we compare two values, let's say I have two people here, John's age, and we want to compare their ages. All right. I have John's age and I have Ed's age. Right. And I tell you that John's age is 24 and Ed's age is 19. All right. And I ask you, who is older? Who is older and by how many years? What are you going to do? Are you going to add these two ages? No. Right? Are you going to multiply these two ages to determine who is older and by how much? No. You're not even going to divide. What you're going to do is you're going to subtract the two ages, correct? So you're going to take John's age, which is 24, and from it you're going to subtract Ed's age, which is 19, and you'll come up with a value of 5, and you're going to say that, well, John is older than Ed by 5 years, correct? If on the other hand, I say, well, let's take another person, Mike's age, all right, Mike's age and Don's age, all right. And I say that Mike's age is 19 and Don's age is 22, right? Tell me who is older. What you're going to do is you're going to take Mike's age, which is 19, and from it subtract Don's age, which is 22, and you're going to come up with a value of -3, correct? -3 is the difference. That tells you that Don is older than Mike, correct? When we have a negative value, for our difference, that means the second value is higher than the first value, right? So we are going to say in this case that Mike is younger than Don by 3 years, or we can say Don is older than Mike. All right. So when we take a difference and we get a negative result, that means the first value is smaller than the second value. If we take the difference and get a positive answer for the difference, that means the first value is greater than the second value. All right. And finally, if we have two values which are the same, so let's say we have 25, two people both have age 25. What will the difference be? The difference is 0. And when the difference is 0, that means both values are equal. All right, so let me write that down. So positive difference means value 1 is greater than value 2. All right. A negative difference means value 2 is greater than value 1, or we should say really value 1 is less, or value 1 is less than, sorry, let me rewrite this, 1, or value 1 is less than value 2, and if the difference is a 0, if it's a 0 difference, that means value 1 and value 2 are equal. Value 1 is equal to value 2. Is equal to value 2. So keep that in mind. All right, is equal. All right, that's how we are going to compare the two values. And throughout this chapter, when we are working with two population means and comparing means, we will talk about difference. It's all about difference. So mu1 minus mu2, that's what you will see throughout this topic. All right. Now we will study the sampling distribution of the difference between two sample means for all possible independent samples out there. Now before we do any study, we have to consider the sampling distribution. When we were studying one population mean, we had to do the same thing. And let me just review that for you for one population mean. For one population mean, all right, we said that the mean of all the sample means will always be equal to whatever whatever the population mean is out there. So the mean of all the sample mean was equal to the population mean. That is for one population. All right, for a single population. The standard deviation of all sample means was given by the formula sigma divided by square root over n, and we said the distribution was normally distributed, normal. But that was for one population. Now that we are working with two population and therefore two sample means for independent samples, let's look at what the distribution is like. Now we said that when we compare two means, we are always looking at the difference of two means. Now keep that big and bold in front of you. We are looking at the difference. So throughout you will see mu1 minus mu2. All right, it's this population mean minus a population mean 1 minus population mean 2, sample mean 1 minus sample mean 2, and so on. So here it says, suppose that x is a normally distributed variable of each of two populations, then for independent samples of sizes n sub 1 and n sub 2 from the two populations, the mu sub x bar sub 1 minus x bar sub 2. So see what they're doing here. They're taking the difference of the two sample means. When we were working with one population, we just had mu sub x bar. Now that we are working with two sample means, it's going to be the difference between the two sample means, and we have to write it as mu sub x bar sub 1 minus x bar sub 2, and that will equal to the whatever the difference is between the two population means out there. All right. Then the standard deviation of the difference of the two sample means is given by this formula, square root over the sigma squared of population 1, which is therefore the standard deviation, the population standard deviation of population 1 squared divided by the sample size of from population 1, so n1, plus the sigma squared sub 2 divided by n sub 2. So this is the formula, and you will see this formula being used in the formulas that we will use, whether to find the confidence interval or whether to perform a hypothesis test. And then the last one always talks about the distribution. So x bar sub 1 minus x bar sub 2 is normally distributed. Okay, now this is for all possible samples. When we work with a particular sample, then most of the time, or in 99% cases, we will not know what the population standard deviation of the difference is. And when the population standard deviation is unknown, we use the sample standard deviation. So you will see these sigmas replaced by the S values, S sub 1 and S sub 2, and we will go through that in the later slides. Now, this is an approach that we are going to take to compare two population means. I had kind of touched upon it in the very first slide, but let's go through it. The example that we are going to work on in our worksheet is to compare the salary of faculty members in private institutions versus the salary of faculty members in public universities. All right, so private schools versus public schools. We want to see who gets paid more or who gets paid less, or if there is no difference in the salaries between the two types of institutions. All right, so there we have population 1, which is defined to be the faculty in private institutions. So we have to make that very clear that we are going to put all private institutions under population 1 and all public institutions going to represent population 2. And then from each of these populations, we are going to draw samples. Again, they are independent. The faculty in private institutions have nothing whatsoever to do with the faculty in public institutions. They don't even know who they are being compared to. All right. So from population 1, we draw the sample 1. So sample 1 contains faculties from private institutions drawn from population 1, and sample 2 consists of faculty drawn from public institutions under population 2. And then once we get our samples and we get the data from each of these samples, we will compute the sample means. So x bar sub 1 pertains to the mean obtained from sample 1, and x bar sub 2 pertains to the sample mean obtained from sample 2. And once we have our data, and of course with these we will also have our standard deviation values, but we are essentially comparing the means. So at the end we compare the two sample means, and come to a decision. And then based on whatever difference we get from these two values, we will use that to project on the two population means. Again, keep in mind throughout we are looking at the difference in the salaries. So you will see everywhere x bar 1 minus x bar 2 being done. All right. Let's look at the z-score formula to compare means of two populations. All right. So when we are working with two populations, we can use the z-value provided the population standard deviation is known. Now, going back to one population, when we were doing our study with one population, what did the z formula to find the z-score look like? It was x bar minus mu population mean divided by sigma over square root over n. The standard deviation part always goes in the denominator. This was for one population. However, now that we are working with two populations, again, we always look at the difference. We are dealing with difference between two means. So instead of just x bar, we will now have x bar sub 1 minus x bar sub 2, and then minus, instead of one mean, we will have the difference between the two population means. Therefore, mu sub 1 minus mu sub 2, and then divided by, in the denominator, we will use this corresponding standard deviation formula. So the standard deviation formula was, if you go back to the slide on the distribution, when we were looking at the sample distribution, it was square root over sigma squared sub 1 divided by n sub 1 plus sigma squared sub 2 divided by n1. So this is going to be the formula we are going to use for the z-score, provided we are given the population standard deviation. Again, in most cases, we will not know the population standard deviation, and we will have to work with the sample standard deviation. So this is going to change a little bit. Now, way back in the beginning of this lecture, when we were going through the goals of this section, we said that there were two possible approaches for performing the inferential study with two population means. And one of them was the pool test, and the other one is the non-pool test. So we'll talk about the pool test first. A pool test can be used when the standard deviations of the two samples are equal or almost equal to each other. All right. So we can use the pool test methodology when the two standard deviations, which will be S1 and S2, are equal. Now, they will never be exactly equal, but if they are close to each other, if they are almost equal, then what we can do is we can combine the two standard deviations into one by taking the weighted average of these and combine them into one standard deviation, which is we'll call as S sub p, which is the pooled standard deviation. So in such cases, we can combine the two standard deviation and pool them into a single value by taking the weighted average of the two standard deviation values. So we will go through the formula to combine these two standard deviation and find the weighted average, which will give us S sub p, and the weighted average will be based on their sample sizes. We are going to weight the two standard deviation values based on their sample sizes, and we are going to come up with a single standard deviation value, which is considered to be the pooled standard deviation. So that's what the pool test is about. In the pool test, we are just combining the two standard deviation, sample standard deviations into one by taking their weighted average based on their respective sample sizes. Now here we talk about the pooled t statistic. Remember, we said we cannot use the z-score, the z distribution in most cases, because we wouldn't know what the population standard deviation is. So we have to work with the sample standard deviations, and whenever we have the sample standard deviations to work with, we use the t distribution. All right. So this is the formula that we will be using for the pooled t statistic. So it says, suppose that x is a normally distributed variable on each of the two populations and that the population standard deviations are equal, because only then we can use the pooled method. Then for independent samples of sizes n sub 1 and n sub 2 from the two populations, the variable t is going to be using this formula where we have x bar sub 1 minus x bar sub 2. That means the difference of the two sample means minus the difference of the two population means. Therefore, mu sub 1 minus mu sub 2. And look at this formula here. It's S sub p. So they have combined the two sample standard deviations into one. They've called it S sub p times square root over 1 divided by n1 plus 1 divided by n sub 2, which are the two sample sizes. All right. And all t distributions work with degrees of freedom parameter, right? So the df formula is n sub 1 plus n sub 2 minus 2. All right, it's no longer n minus 1. That was the formula for df that we were using for one population, correct? For one population. Here we are working with two populations, so it's going to be n sub 1 minus 1 plus n sub 2 minus 1. All right, you have to subtract 1 from each of these sample sizes, and when we combine it, so n sub 1 minus 1 plus n sub 2 minus 1 would be what? N sub 1 plus n sub 2 minus 1 plus minus 1 is minus 2, so it's going to be n sub 1 plus n sub 2 minus 2, and that is what we have here. All right, now we will need to know what the formula is for the pool standard deviation, and we will go through the next slide where we go through each of the steps to perform a hypothesis test, and the S sub V formula will be there. All right, so let's go on, proceed to the next slide to go through the steps of performing a hypothesis test. Now here is the step-by-step process of performing a pooled t-test. All right, now the essential steps, all right, the broad steps of performing a hypothesis test will remain the same. So in step 1, we will have to state the hypothesis. In step 2, we have to decide on a significance level. Then in step 3, we compute the test statistic, and then we will use either the critical value approach or the p-value approach, take a decision, and finally we have to interpret. So those broad steps are going to be the same. The difference will be in how we state our hypothesis. That's going to be a bit different now from what we had learned before, and the formulas are going to be different, and the distribution we use, the table we are going to refer to find the critical values and so on, or the p-value, is going to be different from study to study. All right, so that's what we are going to go through over here, and this is for a pooled test. So let's go through the steps one by one. It says the purpose is to perform a hypothesis test to compare two population means mu sub 1 and mu sub 2. Again, let me drive this into you again, that when we are working with two population means, we are looking at the difference. So there has to be a difference of two means, whether it's population mean or whether it is the sample mean. All right, assumptions, it has to be simple random sample, and that holds true for any study that we perform. Independent samples, they have to be normal population, so the distribution has to be normal, or if it's a large sample, that means a sample size greater than 30 ensures that the distribution is going to be pretty much normal. And number 4, equal population standard deviations. All right, it's assumed to have equal standard deviations or almost equal. All right, now step 1 says the null hypothesis is, this is how we state the null hypothesis. That's what step 1 is. Now here it says H sub 0 colon mu sub 1 equals mu sub 2. All right, so it's going to have the two population mean variables. It's not going to have a value, data value on the right hand side. Earlier, when we were performing our hypothesis test, we said the null hypothesis is going to be mu equals a certain value, 150 or something like that, but that was for one population. Here we are comparing two means, so we have to say that they are equal to each other. Null hypothesis always has an equal sign to it. So essentially what the null hypothesis is saying, that there is no difference between the two means. They are the same. So mu sub 1 equals mu sub 2, and please make sure you Always state your hypothesis with reference to population means. All right, it has to be population notation. Mu sub 1, not x bar sub 1 or x bar sub 2. It's mu sub 1 equals mu sub 2, and they are both in variable form. Do not substitute a value for mu sub 2. Now, alternate hypothesis can be either one of the three. So we can say mu sub 1 is not equal to mu sub 2. In that case, it's a two-tailed test. Or alternate hypothesis can state mu sub 1 is less than mu sub 2, which is a left-tailed test. Or it can say mu sub 1 is greater than mu sub 2, which is a right-tailed test. Step 2, we decide on the significance level alpha, which will be given to us in the question. Then step 3, we compute the value of the test statistic, which is t, using this formula. Again, x bar sub 1 minus x bar sub 2 divided by s sub p times square root over 1 divided by n1 plus 1 divided by n2. And the formula to find s sub p is given by this formula here, where n sub 1 minus 1 times s squared sub 1 plus n sub 2 minus 1 times s sub 2 squared divided by the degrees of freedom formula. Now, remember I said S sub P is the weighted average of the two standard deviations, and they are weighted on basis of their sample sizes. So that's what they have done. They have multiplied each of these standard deviations squared, all right, or the variances, by their respective sample sizes. But when we work with sample standard deviations, we subtract 1 from the sample sizes. So that's why they have n sub 1 minus 1 and n sub 2 minus 1 multiplied by the respective standard deviation values squared. All right, it's variances rather than standard deviation divided by the degrees of freedom formula. Another thing that I want to point out is, remember when we were talking about t equals, the formula for t previously in the previous slide, it was like this: x bar 1 minus x bar 2 minus mu sub 1 minus mu sub 2 divided by whatever the standard deviation formula was, right? Why did they get rid of mu sub 1 minus mu sub 2? All right. Why did they just keep x bar sub 1 minus x bar sub 2? The reason is that mu sub 1 minus mu sub 2 is what the null hypothesis is stating. Now, the null hypothesis stating that mu sub 1 is equal to mu sub 2. So it's saying that since both these two values are equal, this is, if there are equal values, if you take the difference, it's going to make mu sub 1 minus mu sub 2 equal to 0, isn't it? And when we subtract 0 from any value, we are going to have x bar 1 minus whatever that value is, right? Whatever the difference of the sample means is. So that is the reason they have gotten rid of this part of the formula in the numerator. Okay, because the null hypothesis is stating that the two means are equal, and we always subtract the null hypothesis values or whatever the null hypothesis is stating for the means in our formula from the sample means, correct? So that is the reason they have gotten rid, because it will not make any difference, because these two population means are going to amount to 0 when we take their difference. All right, so this is an explanation of the formula. In the next slide, we will talk about the two approaches, the critical value approach and the p-value approach, which you already know from the previous lesson when we were working with one population mean. All right, so that remains the same for critical value. We find our reject regions, do not reject regions, and then we bring our t-score obtained from step 3, which is our evidence, right? Our test statistic, and see in which region it falls. And based on that, we take a decision. If the value falls in rejection region, we reject. If not, we do not reject. And for the p-value approach, we bring our t-statistic, the evidence, find the probability of getting a p-value, and if the p-value is less or equal to whatever the significance level is, we will reject. Otherwise, we do not reject. And finally, we will interpret the results of the hypothesis test. All right, and the interpretation must talk about the difference between the two means. All right, so we will go through an example, an exercise, a worksheet on this particular chapter, on this particular topic, and I will go through the step-by-step process, and it will be more realistic for you at that point. This is a step-by-step procedure to find the confidence intervals for pool T intervals. All right, so again, to find the confidence interval for the difference between two population means mu sub 1 and mu sub 2 is the purpose of this exercise. Assumptions, simple random samples, independent samples, normal populations, or large samples. So it has to be normally distributed, and equal population standard deviations is one of the main assumptions to use the pooled t-interval procedure. Again, the broad steps are the same for performing confidence interval, same as what we learned for one population, except now that we are using a different DF. So the first step is to find the value of T of alpha by 2. We have to split our alpha into 2 because this is a confidence interval, and confidence interval spans on both sides of the center point. And the DF we are going to use to find T of alpha by 2 is DF equals N1 plus N2 minus 2. That is the DF pertaining to two population mean studies. Step 2 is the formula we are going to use to find our interval. So here it's not going to be just x bar, it's going to be x bar sub 1 minus x bar sub 2 plus minus T of alpha by 2 that we find in step 1 times. This is the standard deviation formula for pool standard deviation. So S sub p times square root over 1 divided by sample size 1 plus 1 divided by sample size 2, where S sub p is the pool sample standard deviation. So we will have to use the formula for the pool standard deviation to find the value of S sub p using the two standard deviations. Remember, again, it's the weighted average of the two standard deviations based on their sample sizes. And finally, in step 3, we interpret the confidence interval. Again, we will be working through an example in one of the worksheets for this topic, right? Now, based on the endpoints of a confidence interval, we can make some interpretations about the values of mu sub 1 and mu sub 2, and also relate it with the hypothesis test results. Okay, so case 1 is, the first case would be when the endpoints of the confidence interval are both positive, right? So when we come up with a confidence interval where the interval endpoints are both positive. Again, keep in mind we are talking about difference. All right, we are talking about difference. And when the endpoints of the difference between the two means in the confidence interval are both positive, that means mu sub 1 is greater than mu sub 2. All right, that tells us mu sub 1 is greater than mu sub 2. Now, keep in mind that in our hypothesis test, there's a relation between the hypothesis test results and the confidence intervals that we find. The null hypothesis mean in our tests say mu sub 1 is equal to mu sub 2. Now, if the confidence interval has both positive values at its end or as its end points, that means mu sub 1 is greater than mu sub 2. That means the null hypothesis mean is not equal to each other, because that is saying that mu sub 1 is greater than mu sub 2. In that case, our our hypothesis test will have rejected our null hypothesis. Okay, so based on the endpoints of the confidence interval, we can cross-check, we can verify our results from the from the hypothesis test. If the decision from our hypothesis test was a reject, then the endpoints of the confidence interval should both have the same sign. It could be positive or it could be negative. All right. In case 2, if the endpoints of the confidence interval are both negative, that means mu sub 1 is less than mu sub 2. All right. Remember when we said previously, when the difference of two values, when the difference is a positive difference, that means the first value, value 1, is greater than value 2. And that's what we are applying here. All right. And when the difference is negative, difference, that means value 1 is less than value 2. So that means one mean is less than the other, and that holds true for rejecting the null hypothesis as well, because the null hypothesis will always say that the two means are equal. But if the confidence interval has shown that both endpoints are have the same sign, then that means the means are not equal. We better have rejected the null hypothesis. All right. And the other one is when the one endpoint is positive and the other is negative. So that means that this, all right, so we have a difference of 0. Again, over here, our center point has 0 for a difference, and the confidence interval has one negative on the left hand side of 0 and the other one is positive. All right, so a negative endpoint and a positive endpoint. Now this interval includes the difference of 0 in it, right? It includes a difference of 0. That means that the null hypothesis is true. All right, so the null hypothesis, which says mu1 equals mu2, for it to be true, that means the difference between the two should be 0. And because this confidence interval includes a difference of 0, that means the null hypothesis is true. All right, and in that case, we do not reject the null hypothesis. All right, so these two must be in sync. The results of the confidence interval, and the results of the hypothesis test must be in sync. So if you are seeing that your confidence interval has the same signs at both the ends, but your null hypothesis, or rather you haven't rejected your null hypothesis, and go back and check your results either on the hypothesis test or on the confidence interval, and because they must agree, they must be in sync. This is an example problem of comparing two population means for independent samples using the pooled test procedure. So the problem is about comparing if mean salaries of faculty in private and public colleges are different. Now we are going to go through this study. We are going to do a complete step-by-step process of performing a hypothesis test and finding the confidence interval in a separate worksheet. However, in this particular lecture, I just want to introduce the problem to you and go over some concepts, some basic concepts, or how to answer some basic questions to get started with the hypothesis test. All right. So here it says comparing if mean salaries of faculty in private and public colleges are different. The first question is, what are the variables here? The variable under study is the mean salary. That's what we are studying, the difference in the mean salary. So the variables is salary. And there are two populations here. What are the two populations to consider? We have defined population 1 as the faculty in private colleges, and population 2 is defined as the faculty in public college. So we have to make sure that we first of all define the two population, all right, which college should fall under which population, and accordingly align the different measures that we find uh, with the right population, right? And for the next question, they ask us to denote the means of the salaries. So mu sub 1, which is the population mean, would be the mean salary in private college, and mu sub 2 would be the mean salary in public college, and correspondingly the x bar sub 1 would be the sample mean for the private colleges, and mu x bar sub 2 will be the corresponding sample mean for public college, and then there will be s sub 1 and s sub 2, and therefore n sub 1 and n sub 2. So we have to make sure that these values, all right, are aligned with the right population. Then number 4 says state the hypothesis, the two hypotheses. So h sub 0 colon mu sub 1 equals mu sub 2. So the null hypothesis is always going to say that there is no difference in the means. So the salaries, what it's stating when it says mu sub 1 equals mu sub 2, it's saying the salaries of faculty in private and faculties in private and public colleges are the same. Okay, the salaries are same. There's no difference in the salaries, are equal. And the alternate hypothesis says mu sub 1, that means the salary in private colleges, is not equal to mu sub 2. It could be less, it could be greater, but the wording here in the question says whether they are different or not. So if they had said whether faculty in private schools salaries are greater than public schools, then we would use the greater than symbol here. If it said is less or not, we would use the less than, but it says different. The wording here says different. So that's why we use the not equal to symbol. Now, after we perform our hypothesis test for that particular example, we are going to have to find the confidence interval for the difference of the two population means. That means the confidence interval will tell us within what interval we can expect the difference in the two population means to lie. All right, and then we will also be able to figure out, based on our hypothesis test results, whether one college, or rather whether one type of college, whether private colleges have a higher salary than the public colleges, or whether it has salaries less than public colleges, or whether there is no difference in the salaries between the private and public college faculties, right? So one more time, the inferences for two population means using independent samples with standard deviation assumed equal. The inferential procedure for two population means using independent samples and having almost equal standard deviation. It's called the pool T test. So for this example that we just reviewed, we are going to use the pool T test procedure. So we are going to combine the two standard deviation values from the two samples, take their weighted average, and find S sub P, which is the pooled standard deviation. We have to satisfy these following conditions. First of all, it has to be a simple random sample. It has to be an independent sample. It better be a normal distribution, or if it is a sample size which is large enough, then it's automatically assumed to be a normal distribution, and equal population standard deviations. And I will show you shortly how we can determine whether the two standard deviations are close enough to use the pooled T test. Now this slide shows how we can check the assumptions that were given to us. So assumption 1 is simple random sample. So that would be given in the question. All right. So you have to look for whether it's a simple random sample or not in the question itself. All right. If it is independent sample, that would also be given to us in the question. So look for it in the question. Assumption 3, it either has to be stated to be a normal distribution, again in the question itself, or if that is not given, then check for the sample sizes. If the sample sizes are greater than 30, greater or equal to 30, then it'll be considered a large sample and you can go ahead and use the procedure. Assumption 4 is whether the sample standard deviation are almost equal or not. All right, 26.21 is one of the standard deviations for private colleges, and S sub 2 is 23.95 is the standard deviation for public colleges, and they are almost the same. Now, what is the rule of thumb to determine how close they are? What I would suggest is just take the higher value, take the higher of the two standard deviations, say 26.21, and divide it by the smaller standard deviation value, which is 23.95. All right, and find its ratio. If the ratio, all right, if the ratio of the two values, if that ratio is less than 2, all right, if it is less than 2, then assume that the standard deviations are close enough to use this pooled test. All right, then assume standard deviations are fairly close to use the pooled test. All right, so that's going to be the rule of thumb. Whenever you're given two standard deviations and you have to figure out, all right, whether you can use the pooled test or not, just take the higher standard deviation value, divide it by the smaller value, and see whether the resulting quotient is less than 2 or not. If it is less than 2, then you can go ahead and use the pool test. Otherwise, if it is greater or equal to 2, then you just have to go for the non-pool test, which we will learn later on. All right, so this is the data given to us. These salaries, the mean salaries are in thousands. So 88.19 for the sample mean of private colleges is, because it's in thousands, it's going to be interpreted as $88,190 per year is the average salary of faculties in private schools for this particular sample. And for public schools, when it says X bar sub 2 is 73.18, that means in thousand that translates to 73,180 dollars per year. The standard deviation 26.21 again is in thousands, and N-sub 1, the sample size for private colleges that was used was 35, and for N-sub 2, it is equal to 30, right? So this is the data we are going to work with. Again, as I said earlier, we are going to work this entire problem in a worksheet, and that'll be a separate video, right? But for this particular lecture, we will now go on to the non-pool test when the uh, standard deviations are not close enough to use the pooled test, t-test. We will have to use the non-pool t-test, and that's what we are going to go over in the next few slides. Now we'll talk about the process of drawing inferences for two population means using independent samples when the standard deviations are assumed not equal. So it says here the inferential procedure for two population means using independent samples and not having equal standard deviation, it's called the non-pool t-test. So because the standard deviations uh, different different by a big margin, we cannot combine them into one standard deviation, into a single standard deviation using the weighted average method and all that, which we did for the pool test. We have to keep the two standard deviations separate. And that whole process is called the non-pool t-test, and it uses different formulas, and it also uses different uh, formula for the degrees of freedom. And we will see that shortly what those formulas are. But the assumptions here are that a simple random sample. Then number 2 is it has to be an independent sample, and number 3, normal population or large sample size. Now, one thing I want to mention in this context is that uh, you can use a non-pool t-test for situations when the sample standard deviations are equal. So this non-pool t-test can be used for any circumstances, whether the standard deviations are equal or not equal, right? But the pool t-test you cannot use when the standard deviations are different by a wider margin, right? So this is an application problem, word problem for non-pool t-test. Again, we will work this in a worksheet. It'll be a separate video I'll put up, but this is the example. Let me introduce the example to you. It's a neurosurgery operative times, whether a dynamic system, a Z plate, reduces operative times relative to a static system. So they're talking about two different procedures to perform a neurosurgery, a surgery, and they want to see the effect of using the two different uh, ways of performing the surgery, what the effect that has on the time taken to complete the surgery. So neurosurgery operative time. So one method is to use the dynamic system method, and the other one is to use the static system. I don't know what those systems are, but let's just go with it. And they want to compare the time taken to perform each of these surgeries, and they want to know if it reduces, if the dynamic system takes less time than when using the static system. Again, same questions here. What are the variables here? What is the variable? It's only a single variable for, even though we have two populations, the variable under study is going to be one. And in this case, the time, the surgery time, basically. Number 2 says, what are the two populations to consider? We have to define population 1 and population 2. Let's assign operation using the dynamic systems as population 1, or assign it to population 1, and operations involving the static system, let's assign that to population 2. Now, in Now question number 3 asks to denote the means of the two systems. So the mean time taken using the dynamic system would be denoted as mu sub 1, and the mean time using the static system is denoted as mu sub 2. So, and that should align with the two populations that we defined earlier. And then to state the hypothesis, the null hypothesis H sub 0 again must say that the two times, the mean time using the dynamic system and the static system are the same. It should always have an equal sign in it. And again, I'll remind you that you always have to state your null hypothesis using the population parameters. All right, it has to be mu sub 1 and not x bar sub 1 and x bar sub 2. So mu sub 1 equals mu sub 2, and the alternate hypothesis should be mu sub 1 is less than mu sub 2. Why less than mu sub 2? Because the question says we want to test whether the dynamic system reduces the operative time. That means reduces means it lessens the operative time relative to a static system, right? Let's check the assumptions for the non-pool test. Assumption 1 was simple random sample, and that we have to find from the wording in the question given to us. And all studies must be simple random samples, all right? Otherwise, it's not valid. We cannot even proceed to the next assumptions. Now, for this particular problem also, it has to be independent samples, and that should also be given in the question. Again, assumption 3 is about the distribution. It has to be a normal distribution. That too has to be stated somewhere in the question. So look for it in the question itself. And if that is not given, then check for the sample size. The large sample size. Here the sample size is given are 14 and 6, and they are not large enough. So somewhere in the question it must say that this is normal distribution. I don't have the whole question written out here, but let's assume that it is a normal distribution. This problem is from the textbook, so you should be able to look that up, the details of this particular problem. And then finally, it's okay. It says here for assumption 3, normal distribution on large sample. So even though the sample sizes are too small, the normal probability plot showed no outliers. So that must have been given in the wording of the question. All right. And then non-pool test is robust to moderate violations of normality. We can use the non-pool test because it can be used for moderate violations of normality. So that is something, kind of a fact. All right, so just know that. And if we look at our S sub 1 and S sub 2 values, all right, we will see, remember what I said about the rule of thumb to determine whether the two sample sizes are close enough to use the pooled test or not. You take the higher standard deviation value, which in this case is 84.7, and divided by the smaller standard deviation value, which in this case is 38.2. And if it is less or equal to, or well, actually if it's less than 2, then we can use the pooled test. If not, we will have to just use the non-pooled test. So 84.7 divided by 38.2 is greater than 2. All right, if you do the division, you'll find that it is greater than 2, and that's why they are not close enough to use the pool test. We will have to just use the non-pool test. So that's the way we figure out whether we can figure out which test we should be using. This slide gives us the distribution of the non-pool t-test. It says suppose that x is a normally distributed variable on each of two populations. Then for independent samples of sizes n sub 1 and n sub 2 from the two populations, the variable of t, that means the t distribution, has this particular formula, which is x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2, which will vanish when we perform the hypothesis test and use this formula to find the t uh, t value, the test statistic value. But look at the formula for the denominator here, the standard deviation part of it. We cannot combine the two standard deviations, right, in a non-pool test because they are widely different. Instead, we have to keep them separate. So S sub 1 squared divided by N sub 1 plus S sub 2 squared divided by N sub 2, and we have the square root sign over it. So this is the formula we are going to use when we perform a hypothesis test. And however, the degrees of freedom formula is a bit complicated. So the degrees of freedom is denoted by this symbol delta, which is a Greek symbol, and this is the formula we use to calculate the df. All right, because we are keeping the two standard deviations separate, we have to use this special formula to find the df. Now this is a rather complicated formula. However, in the tests, I may just give you the value of the degrees of freedom, so you do not have to perform this calculation within time constraints in an exam. However, just see that this whole entire formula just works with the two standard deviation and the two sample size values. All right, so in the numerator we have s squared, so s sub 1 squared divided by n1 plus s sub 2 squared divided by n2, and we square this entire expression, and in the denominator we have a complex fraction, so to speak. We have s squared divided by n sub 1 squared over n sub 1 minus 1 plus s sub 2 squared divided by n sub 2. This whole thing squared divided by n sub 2 minus 1. Again, when you're working on your homework, you may have to do the calculation. However, in the exams and the test, I will give you the value of the delta, and you may just verify it through your calculators, but again, it will be provided. All right, so you don't have to do this calculation within time constraints. Here's the step-by-step procedure to perform a non-pool t-test. Purpose: to perform a hypothesis test to compare two population means, mu sub 1 and mu sub 2. Assumptions: simple random samples, independent samples, and normal populations or large samples. First step is to state our hypothesis. The null hypothesis will always say that the two means are equal, so mu sub 1 equals mu sub 2, and the alternate hypothesis could be either one of the three. It could either say that mu sub 1 is not equal to mu sub 2, or it could say mu sub 1 is less than mu sub 2, or mu sub 1 is greater than mu sub 2, in which case it'll be a right tail test. If it's less than, it'll be a left tail test. If it is not equal to, it'll be a two tail test. So that's how we will be stating our null and alternate hypothesis, all right, comparing the two means. Step 2, decide on the significance level alpha, which will be given to us in the question. Step 3 is to find the test statistic, or what is called the evidence in an hypothesis test. And as you can see in the numerator, they have gotten rid of the minus mu sub 1, all right, that minus mu sub 1 minus mu sub 2 is gotten rid of because the null hypothesis says they are equal, and if both mu sub 1 and mu sub 2 are equal, that means this will have a value of 0 and it will not have any effect on x bar sub 1 minus x bar sub 2. All right. And then in the denominator, we have square root over the formula for the standard deviation of two population means. All right. And we denote the test statistic with the symbol T sub 0. In step 4, we use the two approaches to come to a decision. The critical value approach, again, we first have to find our reject and the do not reject regions, or rather we have to draw a diagram showing the reject or the do not reject regions, and for that we have to know the value of delta, this df, using this formula. And once we have this delta value, we find the t of alpha with a df or whatever delta value is. And if we are using the p-value approach, then we have to find the probability or the area associated with our test statistic, all right, with this particular df value, delta value. And then based on what we find from these two approaches, we will either reject the null hypothesis or not reject it and finally interpret the results of the hypothesis test. Now I'm mentioning this, that there'll be a separate video posted on the worksheet showing the example that we just talked about, the dynamic system versus the static system operative times for neurosurgery. We will work that through step by step using all these steps to complete the hypothesis test and later on also find the confidence interval. To find the confidence interval, the t-interval procedure for a non-pooled test, or rather a non-pooled procedure, the broad steps are going to be the same. That is, we have to find our t of alpha by 2 if we are using the t distribution, or the z of alpha by 2 if we are using the z distribution. But for chapter 10 for two population means, we will only be using the t distribution, the t table. All right. So the step 1 is to find t of alpha by 2 with df equals delta, and delta is calculated again using this formula. And then once we know our t of alpha by 2, we will use this formula given over here, x bar 1 minus x bar 2, which is the difference of the two sample means, plus minus t of alpha by 2 times square root over s sub 1 squared divided by n sub 1 plus s sub 2 squared divided by n sub 2, and interpret our confidence interval. Now, choosing between a pooled and a non-pooled T procedure. It says here, suppose you want to use independent simple random samples to compare the means of two populations. To decide between a pooled T procedure and a non-pooled T procedure, follow these guidelines. If you're reasonably sure that the populations have nearly equal standard deviations, use a pooled T procedure. Otherwise, use a non-pooled T procedure, because non-pooled T procedure can be used whether the standard deviations are close or widely different. All right, you can use the non-pooled T procedure in either case. All right, however, the pooled T procedure can be used only when the standard deviations are close enough, and I gave you the rule of thumb to decide. Just look at the ratio of the higher value and the lower value, and if it is less than 2, go ahead and use the pooled procedure. Otherwise, use the non-pooled T procedure. We are now going to talk about the inferences for two population, but this time using paired samples. Previously, we talked about independent samples, but now we will discuss how we can perform an inferential study using paired samples. Now keep in mind, in paired samples there is a relationship between the two populations. All right, they are naturally related. That's what paired samples is about. So we will do a study on that, and then go through the step-by-step process of how to perform an inferential study of paired samples. Now let's quickly review what paired samples is about. A paired sample is appropriate when the members of the two populations are or have a natural pairing. For example, husband and wife. They are related by marriage, brother and sister, right? They are genetically related, correct? So that kind of relationship, if we want to compare the characteristics between husband and wife, a certain particular characteristic between husband and wife, we have to make sure that in sample 1 the husband is a part of that sample, and in sample 2 the wife of that husband who's in sample 1 is included. All right, and same thing if it's a study on a brother and sister, or between two brothers or two sisters, siblings, and so on. Now, each pair in a paired sample consists of a member of one population and that corresponding member in the other population. And that's what I was just telling you, that if you choose a person who's a husband in population 1, you have to make sure that his wife is also included in sample 2. All right, so so that's what paired samples is about. Now, paired samples is not necessarily just between people. It can be between other items too, animate or inanimate items as well. So let's look at this example study. It says comparing two population means using paired samples. What are we studying? The ages of married people in the US. Suppose we want to decide whether in the US the mean age of married men differs from the mean age of married women. So what they have done here is they have shown us the data, and they have chosen about 10 couples, and in the sample. So we have here sample 1, right, from that came from population 1, and sample 1 is all the husbands selected, and sample 2 will have all the respective wives. Okay, so we have here the list of ages. We are studying age, that is the variable, right? It says mean age, that is the variable under study. So they have surveyed the age of the husband, and then they've also surveyed the age of the wife of that husband from sample 1. So we have all these different ages listed here. Now, here we have sample 1. However, we cannot work with a, a single x bar value. So let me just erase this. Okay, we cannot take the mean of all the ages of the husband and come up with a single x bar value. Okay, neither can we just sum up and find the mean of all the wives' ages and come up with an x bar too. All right, because we are comparing the age of each couple. So what we have to do is we have to take the difference at each individual couple. So 59 minus 53, 21 minus 22, 33 minus 36, and calculate the difference. That will give us the difference in the ages and list them in a separate column. Okay, so again, let me repeat this. We cannot do just x bar sub 1 minus x bar sub 2, which we could do for independent samples, because we are comparing at each individual sample level, in this case each couple, we are comparing the age of the husband with the age of his wife, we have to find the difference at each itemized level and record the difference. So 59 minus 53 is 6, 21 minus 22 is -1, 33 minus 36 is -3. So that's how we come up with the difference in the ages at each couple level. And then once we find all the differences, we will sum them up to find the mean difference. All right, so in paired samples, we do not find the sample mean of sample 1 and then the sample mean of sample 2. Rather, what we work with is the mean difference in ages between a husband and his wife. All right, so they have summed up all the D values, difference denoted by D, and then they will find the mean difference. So D bar, just like X bar means sample mean, D bar is the mean difference. Anything with a bar on it in statistics suggests mean. So we have to find the mean difference, and the mean difference would be the same formula, but this time it will be the sum of all these individual difference values, and that was 36. So it will be sigma D, sum of all the differences, divided by n, which is 10. So we are going to have a mean difference of so 36 divided by 10 is going to be 3.6. Okay, so keep in mind when we are working with paired samples, it's no longer X bar sub 1 minus X bar sub 2, which we did for independent samples. For paired samples, we have to first calculate the difference at each individual level, and then we will sum that up to find the mean divided by the number or by the sample size. So let's look at the questions here in order to formulate the problem. The first question is, what is being studied here? It's the difference in ages. What are the variables here? There's of course only one variable, which is the age of married couple. What are the two populations? Population 1 will be all married men. Population 2 will be all married women in the US. And then let mu sub 1 and mu sub 2 denote the means of ages of the two populations. Mu sub 1 would be the mean age of married men, and mu sub 2 would be the mean age of married women. And the hypothesis test statement would be the same as what we used for the independent samples. So the null hypothesis is going to say that the two means are same. There's no difference in the age of married men and married women. So mu sub 1 equals mu sub 2, and alternate hypothesis, because we are studying the difference in age, it's going to be not equal to sign. So it's going to be mu sub 1 not equal to mu sub 2. The assumptions that need to be satisfied for paired samples are relatively simpler than with independent samples. The first one is it has to be simple random samples, which holds true for any statistical study. And then number 2 is normal differences or large samples. The distribution of the paired t statistic, let's look at the equation that we are going to use in order to find our test statistic. It says here, suppose that X is a variable on each of the two populations whose members can be paired. Further, suppose that the paired difference variable D is normally distributed, then for paired samples of size n, the variable t is equal to d bar, which is the mean difference. And a couple of slides before, we kind of quickly ran through how to find the mean difference. You just have to find the difference at the individual level and then sum them up and divide by n. All right, so d bar, that's what would be the mean difference, that's d bar, minus mu sub 1 minus mu sub 2 divided by s sub d divided by square root over n. So S sub d is the standard deviation of all the differences that we recorded in the last column of our table. So we have to calculate the standard deviation of those differences as well. So not only just the mean, but also the standard deviation, and then divide that by square root over n. The df we are using again is just n minus 1. No longer n1 plus n2 minus 2 or that complicated uh, delta formula that we used for non-pool test. For this one, it's very simple. The df is just n minus 1, and the formula is d bar minus mu sub 1 minus mu sub 2 divided by s sub d divided by square root over n. When we are performing a hypothesis test, this is going to go away because the null hypothesis is going to state that mu sub 1 equals mu sub 2, and when that happens, if the two means are equal, that means their difference is going to be a 0. And for the hypothesis test, just for the hypothesis test, we are going to end up having d bar divided by s sub d over square root over n divided by square root over n with df n minus 1. Now, what are the steps that we should follow in order to perform a hypothesis test for paired t-test? Assumptions, again, a simple random paired sample and normal differences or large sample. First, state your hypothesis. The null hypothesis is stated as mu sub 1 equals mu sub 2, and there are three different ways of stating the alternate hypothesis. Either it can be not equal to, so mu sub 1 not equal to mu sub 2 would make it a two-tailed test. Mu sub 1 less than mu sub 2 would make it a left-tailed test, and mu sub 1 greater than mu sub 2 is going to make it a right-tailed test. Step 2 is to come up with the significance level alpha, which we are going to which is going to be given to us really. And step 3 is compute the test statistics, which is our evidence that we bring to the table, correct? And when performing a hypothesis test, the formula is T equals D bar. Like I said previously, they have taken out the minus mu sub 1 minus mu sub 2. All right, so we just have D bar divided by S sub D, the standard deviation of the differences, divided by square root over n. And then once we find our evidence, we use these approaches, the critical value approach, where we define our reject and do not reject regions. We find the critical values and we use the T distribution, all right? And the DF that we use, the formula that we use is going to be n minus 1, or we can use or rather we can use the p-value approach, where we bring our test statistic and find the probability of getting the probability of getting that value, that particular value for the test statistic, assuming the null hypothesis is true. And once we perform those two approaches, based on its results, we will take a decision whether we should reject the null hypothesis or not reject the null hypothesis, and finally interpret the results of the hypothesis test. Let's quickly run through the formula to find the confidence interval. To find the confidence interval for the difference between two population means, mu sub 1 and mu sub 2, we have to first, of course, satisfy these two assumptions that they are simple random samples, paired samples, of course, and then it's either a normal distribution or a large sample. And then for step 1, we first have to find T of alpha by 2 with df n minus 1, and then use this formula d bar plus minus t of alpha by 2 times s sub d divided by square root over n. That's the formula we use to find the end points of our interval. And then once we have the endpoints, once we find our confidence interval, we will just interpret the interval in context of the problem that we work on, right? So again, I'm going to work on example problems. Actually, this particular problem on the age difference in husbands and wives in the US in a separate worksheet. So just look for that video, all right, to see how we work through it step by step.